Hello, here is secondary chemistry with a video on changes of state. You should already be familiar with the three different states of matter and their particle diagrams. We have made a video on this topic earlier because now we are looking at the changes between those states. If you have a solid and you turn this solid into a liquid, the process undergone is called melting. And the opposite process, so turning a liquid into a solid, is called solidifying or freezing. The state of a substance doesn't change randomly, but we either have to heat the substance or to cool it down. In other words, changes of states involve energy changes. And we can exemplify this when we look at butter. So melting butter, turning solid butter into liquid butter, requires energy. We all know this from our daily life experience, and that's why we put butter into the hot pan when we want to melt it and not into the deep freezer. But why does the process of melting obviously require energy? To answer that question, we have to look at the particle diagrams of solid and liquid butter. And the major difference between solid butter and liquid butter in terms of the particles is that the distances between the particles have increased. And you know that particles attract one another. We can imagine this being similar to attraction forces between magnets, kind of. And if you try to pull away two magnets from one another, then this will be hard and require energy. And similarly, you have to provide energy to separate attracting particles from one another. And thus, during melting, the energy is used to overcome attraction forces between the particles. So we can conclude that the process of melting in general takes in energy because particles have to be separated. So no matter whether I melt butter or water or any other substance, I have to take in energy because always particles have to be separated. I hope you are getting this point. Here's another example of melting. If we have a portion of ice cubes, we can melt them and turn them into liquid water. We have seen from the previous slide that the process of melting requires energy, and this can be written down using the notation you can see right here. Delta H equals plus 167 kilojoules. And delta H corresponds to the energy difference. So that's the amount of energy, in our case, needed to make the ice cubes melt. 167 kilojoules. But of course, we can also take the liquid water and solidify it and turn it back into solid water. Then we will also observe an energy change, and that energy change will be delta H equals minus 167 kg. That's interesting to note that we have an opposite sign here, because this means that the same amount of energy that is needed to melt the ice cubes will be released when the same portion of water solidifies again. And maybe that idea sounds a bit weird to you, that solidifying water releases energy, but in fact, this thing is even applied in agriculture. So farmers who are growing grapes in cold regions, they do something which has to do with the thing we are just talking about. So let's imagine this circle being a grape. And when farmers expect a cold night, then they sprinkle some liquid water onto the grapes. And this water solidifies and forms a layer of ice. But during the process of solidifying, heat energy is released and the grapes don't get that cold. And the layer of ice also prevents the grapes from getting too cold if they are exposed to let's imagine we have negative temperatures outside, then even the ice layer has a protective function. But anyway, solidifying gives out heat energy. There's one more thing I want to mention briefly, and this is if delta H is positive, so this plus sign over here, then you know that energy is taken in. And if delta H is negative, then you know that energy is given out. Please don't get headache about it. This is simply a thing of definition, and it should once be accepted and applied correctly. The takeaway from this slide is that opposite changes of state, like melting and solidifying, are also opposite in terms of energy. So one direction requires energy, the other direction releases energy. Okay, let's extend our diagram and consider gases now. Turning a liquid into a gas is usually called boiling, and turning a gas into a liquid is called condensation. Okay, but some of you might have heard about evaporating before. What's the difference between boiling and evaporating? Or let's maybe start with the first question. What's similar between boiling and evaporating? And this is the fact that during both processes, liquid water is turned into gaseous water by the means of heat. The difference is that boiling occurs at a fast rate. So if you boil water for cooking, then this will take you maybe some minutes. But evaporating happens at a slow rate. If you dry your laundry, that usually doesn't happen within minutes, but rather within hours or days. And the second difference is that boiling happens at a specific temperature, and this is the so-called boiling point of a substance. So the temperature where a liquid changes into a gas, and similarly the melting point is the temperature where a solid turns into a liquid. And evaporating happens over a temperature range. So the boiling point of water is 100 degrees Celsius. But our laundry apparently doesn't have to be exposed to 100 degrees Celsius to dry. The water can also turn into gaseous water below 100 degrees Celsius. That's why we say the water evaporates, because it happens slowly and over a temperature range and not just at the specific temperature, namely the boiling point of a substance. Yeah, and there's also another application of evaporation and also condensation, so kind of the opposite process, and this is the water cycle. Within seas and rivers and lakes, we have liquid water, and this water evaporates through the sun. So that tells us now that the process of evaporation happens slowly and over a temperature range. So water from seas and lakes evaporates even below 100 degrees Celsius. And as the water is moving upwards in the atmosphere, it cools down, and at some point it condenses to form clouds. And during condensation, of course, heat energy is released, because it's easier to look at the process of evaporating or boiling. To turn liquid water into gaseous water, you have to separate particles. I want to illustrate this to you again. So this is a particle diagram of liquid water. So I put a lowercase l in brackets to show the state symbol of a liquid substance. And when we turn a liquid into a gas, this is a lowercase g for a gas, then the particles are even more separated. So once again, attraction forces have to be overcome. So turning a liquid into a gas will require energy. Boiling and evaporating requires energy. That's why we need the sun. That's why we need the stove to provide heat energy, to provide thermic energy. But that also means that the process of condensation, so turning a gas back into a liquid, will release heat energy. And that's what you can observe when you put your hand on top of boiling water. It gets hot because you feel the warmth of condensation. Water is condensing at your hand, so gaseous water turns back into liquid water on the surface of your hand, and then you feel heat because that process of condensation releases heat. But let's go back to the water cycle. So we have arrived there where we can see the formation of clouds, and at some point the clouds will allow rain to fall, and liquid water arrives at the surface of the earth again, and through rivers and lakes the water eventually ends up in the seas again, and the water cycle is closed. So the water cycle is also an example of evaporation and condensation, two changes of state. Let's finish our diagram. There's also a change of state, solid to gas. It's quite uncommon because we kind of skip the liquid state of matter, but it is existent, and we call this change of state sublimation. The opposite process of having a gas that directly turns into a solid is called deposition. And a substance which sublimes and deposits is carbon dioxide. That's what you can also see at the picture. On the spoon we have a block of solid carbon dioxide, and solid carbon dioxide is existent at temperatures below minus 77 degrees Celsius. If we have a temperature hotter than minus 77 degrees Celsius, well, hotter is relative because even minus 70 degrees is cold, but still at temperatures above minus 77 degrees, the solid carbon dioxide directly turns into gaseous carbon dioxide, and it skips the liquid state of matter. And equally, if we have gaseous carbon dioxide, for example from the atmosphere, and we cool it down below minus 77 degrees Celsius, we will observe gaseous carbon dioxide directly turning into a solid, so it deposits. That's all you have to know about the changes of state. I hope this was helpful, and I'm looking forward to see you in the next video.